Hi. Hello. I would like to explain a little bit more about how to read uncertainty when it involves graphs. Indeed, I'm going to try to give hopefully a better explanation of something that we already covered in uncertainty videos and also in the lectures. It was related with the uncertainty here in fanning friction factor. So basically the idea is this: we can generalize this question. We can compute uncertainty in a quantity in X, let's say here. We can compute the point estimate, and we can compute the uncertainty associated with that point estimate. That is the question. What is going to be the associated point estimate? The associated point estimate is, of course, easy because we are just going to read whatever this line is going to correspond to here, this point. But what is the associated uncertainty factor in y-axis? That is the question. And I have already, as I said, tried to explain this previously, but let me try to make it hopefully a little bit more clear. Basically, the derivation starts here. We would like to compute this quantity, uncertainty in BF. I'm sorry, fanning friction factor, which is the bias in fanning friction factor square. So first of all, it's always a good idea to start with the point estimate. The point estimate is computed here. So the Reynolds number is computed as 16,000. So it's going to be 10,000 here. 16,000 is going to be somewhere here, hopefully. And note that when I even show this, there's going to be some uncertainty related with the resolution. So if you pull a straight line here, which should be much more, of course, straight than this one, and then this one, basically, I guess somewhere here is going to be our F value. And for some reason, I read this as 0.028, let's say. As you can see, one can easily read this as 0.025 or maybe even lower. So there's pretty much uncertainty even here, but this is not a very good, as you can see, straight line. So anyway, this is going to be, let's say, our point estimate. And repeat again, you can come up with different point estimates. Now the question here is including the uncertainty related with resolution here in x-axis and also in y-axis, and also the point estimate in Reynolds number. How are we going to come up with a bias or uncertainty in fanning friction factor? So we are just going to stick to the equation. The equation simply is going to say that bias in friction factor square is going to be equal to Reynolds number square plus bias in Reynolds number square, and that's plus BR square, resolution value. So one may easily think about this term as bias in friction factor due to the difference or the uncertainty in Reynolds number plus bias due to resolution, and bias of fanning friction factor due to resolution square is indeed going to be formulated with this expression. Now note that so we can do a couple of things here. Either we can compute this quantity, right? Or we can write this quantity in simpler terms. So what I did here is a kind of, I did it maybe a little bit faster than it should be. Basically, you can do it in this way. Reynolds number square is going to be equal to, since Reynolds number here is going to be a function of velocity and diameter. Note that, remember, we had density and viscosity constant, but in your project it may not be. Indeed, they may change with respect to different temperatures because temperature does not seem to be known very well. Anyway, so this is going to be equal to Reynolds number partial derivative with respect to u square bias u square plus Reynolds number with respect to diameter square bias in diameter square. Indeed, these terms are exactly equal to those. But now I approach the problem maybe from a more general case. So bias in Reynolds number is going to be equal to these quantities. So Reynolds number with respect to velocity when you take the derivative is going to be equal to diameter mu square times du square plus, when it comes to diameter, this is going to be density average velocity over mu square bias in diameter square. So this is going to be the uncertainty square in Reynolds number. And we already know all of these values. We know that the bias in U was computed some prior value, which I cannot remember. And these values are already known. And bias in diameter square is already known. I think these are the values. Yeah. You can feed this value here. And you can feed this value here. And when there you are going to take the squares, then density, viscosity, and diameter and velocity are going to be replaced with the corresponding values. So basically, this value is found to be equal to 923 square plus, and this value is going to be equal to 390, which is going to be square. So basically, if we sum these two values, Reynolds number square, so I need a calculator for that. Let me pause this video and find a calculator. Okay, using the calculator, we can find this value to be equal to 1002 square. So basically, this first of all says that Reynolds number, the bias in Reynolds number is about 1000. And compare it with the value that we have already calculated for Reynolds number. Where is that value? It was 16. Yeah. So the point estimate of Reynolds number was 16,683, which, for instance, is going to mean that Reynolds number can be equal to, or is going to be in plus minus 2000. So if you would like to come up with an uncertainty point estimate of Reynolds number and the associated uncertainty, it's going to be somewhat like that. Now we are going to apply this Reynolds number, uncertainty Reynolds number, and resolution to the y value, which is going to be the friction factor. So basically here, from now on, the idea is, now forget about the equation. I'll come to that, but forget about the equation for the time being. Do I have a red colored? Yeah, I should be, okay, whatever. So basically, let's say that we are at this point. Let me get rid of here. It's going to be somewhat like this. Bias is this value. I'm talking about 1000 here. Plus minus 1000 is going to be somewhat like this. So if we are talking about a straight line, such as this one, it's going to be indeed between two of these here, this one and this one. So what I indeed do is, can I draw a straight line like this using shift or something like this? Let me try. No, I cannot do it. Anyway, so it's going to be, so what I'm trying to say is that this is going to be, we are going to find the point here that's going to be, that's going to correspond to 16,683 minus 1,000, which is going to be 15,683, wherever that point corresponds to. And this point is going to be 16,683 plus 1,000, which is going to be 17,000, whatever. So the corresponding y values are going to be found here. So what you can do here is find the difference between those two and then divide by 2. So basically, it seems to be somewhat like 0. 0. I don't know, like 0.00, or let's say 2 or 3, and divide by 2, it's going to be 0.001. So this is going to be the bias, which is going to stem from this part. So this part is going to be replaced by, for instance, 0.00. Do I need another 0 here? Let me check. 0. This one is going to correspond. No, 001 square. Now you may easily say that where is that formulation? I mean, why didn't we use this value? Why didn't we use computed this value and take the square? Instead of that, we did that tricky kind of thing. Here I'm going to do that, and I'm going to show you these are indeed mathematically, this is exactly what this procedure corresponds to. But understanding this procedure when it comes to graphical methods is much more easier. I repeat again, find the bias here in x-axis, then find the corresponding, for the upper and lower limit, find the corresponding y values, and find the difference between those two and divide by 2. Why divide by 2? Because plus and minus, we have bias terms around the center point here. So therefore, when we find these values, we kind of assume that the center point is going to be the middle way between those two. And note that, as you can see, since this is going to be a non-linear mapping, although in a small region, this is going to somehow, the approximation is going to be valid. That's the reason why we divide. So actually, it's one bias here and one bias here. It's going to be 2 bias this width. This width is going to be also 2 bias. Therefore, that's the reason why we divide by 2, and we get the bias in y value. Then here is going to be the, indeed, this is what we compute here. Bias in friction factor due to Reynolds number. We need the square of this. Therefore, we take the square and add with the resolution. Let me finish this. When it comes to resolution, it may be even much more higher here, because there is actually a resolution bias also coming here, not also only this one, because we do not know exactly where 16,600 whatever is. So I kind of come up with an estimate here. I do not know where this one is exactly, and I do not know where this value falls exactly. I think a bias value, something like 0.003 or 2 may be sufficient here. So which means that if I read a value here as 0.0, I don't know, maybe 25, this could be 28 or maybe 22. So this seems to be pretty much sufficient, also including this x-axis. Note that if you would like to do it more rigorously, then you have to come up with a bias here in x-axis, then propagate it to y-axis again. You can do it, but I don't think that's that much important here. So that much of a bias, 0.003, seems to be sufficient. So this is going to be equal to 0.003 square. So you are going to take the square of these two, and this is going to be the value that we obtain. And let's, if I can find it, 0.003 square plus 0.001 square, and square root of that value is going to be 0.003. So this value is going to be somewhat like 0.0033 square. So therefore, when we take the square root, bias in friction factor is going to be somewhat like 0.003. And it's going to be coming, most of the problem is going to be due to resolution in reading this graph. Note that if you are much careful with that, if you can guarantee that you can read these 16,000 value here and the friction factor value here logarithmically, which is not very easy, but maybe you can use a higher resolution ruler, you can reduce this value, right? So here, this seems to be the dominating factor. Now let's come back again. The problem may seem to be, I used a kind of practical approach to compute this quantity, indeed this quantity here, which is equal to this one. Can we use this quantity here to compute this quantity? Yes, we can. the bias in Reynolds number square, we have already computed it to be equal to 1002 square value. Okay, so now this indeed means at that point, at the estimated point, how does Reynolds number change? How does friction factor change with respect to Reynolds number? Indeed, the slope here should be predicted. So one can say that, okay, I'm going to read the slope here. Well, you are welcome to do so, but let's not do it yet. Let's just continue. If you write it in this fashion here, F Reynolds number, which is the slope, times square. So I take into this bias here multiplied by the square. Then we take this multiplied by the bias with the slope, then take the square. We are going to be multiplying here this slope with the bias in Reynolds number, which is indeed equal to 10,000. I'm sorry, 1,000. So slope times 1,000, and note that that 1,000 is the deviation from the estimated value, that deviation in the right-hand side. So it's going to be basically, which is going to give us this lower value here. So when you also multiply by the left-hand side, it's going to give the upper value here. So basically this operation simply, just when we apply it for one side here, then take the square, basically we are just finding this delta F value and then taking the square here, which is exactly what we do here. 0.001 is not exactly, but very roughly what we do here. We find 0.02 and divide by 2. Therefore, we find the deviation in one side is 0.001. We then take the square here, which is very similar to what we do here. So basically, finding the slope and multiplying by bias, then taking the square, which is indeed the operation here is indeed find the deviation in one direction, propagate that deviation to y-axis, then take the square. And this is practically what we have done here. That's why you do not need to find the partial derivative of slope here and multiply, because actually one may think that this is much more rigorous. It is not, because while taking the partial derivative, this is going to be even much more problematic. There is going to be an additional uncertainty while you are trying to find the slope here by using visual methods, because you are going to use a ruler, you are going to try to come up with a tangent line, you are going to try to find the slope. Is going to be even, it's going to be more erroneous, less accurate and precise, quite probably. But as I said, they lead to this very same result. So what I can say that generally this should be the procedure that you are following. If you like, you can write the equations, but I believe writing these equations this way is pretty much sufficient. So BF square is going to be indeed equal to BF square due to Reynolds number, perturbation in Reynolds number, or uncertainty Reynolds number, plus B resolution square. When it comes to this, it doesn't need to be always Reynolds number. Note that we can write it for any y and x. So py square is going to be equal to py square x B resolution. This may be the usual formulation here that you may use, which says I would like to find the uncertainty in y. And where is my cursor? Cannot find it. Anyway, uncertainty in y square is going to be equal to, yeah, I found it. Uncertainty in y square, uncertain square in y is going to be equal to uncertain square in y due to uncertainty in x. How much of is that propagated? And the way to find it is to find the uncertainty in x. And this is what we have done here. And then instead of using any equation or something like this to go from this side to this side, from this point to this point, use the graph. Here, just label the uncertainty range then come up with this band here, right? Plus and minus values, and propagate these plus and minus values here and come up with the bias here in y value, then divide by 2 to find the bias in y value. And then when it comes to resolution, come up with a convenient estimate. Well, if you would like to, for those who would like to be much more precise or rigorous in resolution, indeed, this is a little bit more involved. We should say that this resolution indeed consists of, let me write here, resolution in y and resolution in x. So this is going to be the bias due to uncertainty, bias in resolution due to uncertainty in y, or uncertainty in the resolution of y, uncertainty resolution of x. And this is going to be a little bit more involved. This is going to be indeed equal to a propagation of resolution in x. How much of that is propagated to y? Actually, I'm going to stop here, but I think you got the idea here. So how much error do we commit here? Then this error is going to be propagated to a certain also width here in y value. So this is going to be estimate of that value, and this one is going to be directly how much error are we committing here while we read the y value. So this is even a little bit much more involved. For this case, it's not, I don't want that much detail from you. That's okay, but please realize as a detective work, try to understand where all of each of these sources creep from different directions to your calculations and may affect the result of your calculations. Anyway, for that specific example, resolution seems to be the more dominating factor. So if I were you, for instance, I would maybe use a ruler here, but it is difficult to use a ruler because this is in logarithmic scale. So maybe try to come up with a logarithmic scale ruler so that you can read these values more precisely, because this seems to be the dominating factor which determines the high bias or bias in friction factor value. And please also note that we have not included anything related with the pipe roughness. So if we are talking about, for instance, a region such as this one, 0.01 to 10 to the power minus 6. Oh, by the way, it would be a good idea to see what this roughness in physical terms corresponds to. You may search for instance, pipes with a roughness 0.01. What do they look like? Do they look like the things that we have seen in that project? So anyway, if this is the case, then we are talking about a much wide range here. And this is going to be the highest dominating factor here, because there's going to be also plus, let's say this is going to be a bias due to roughness, and this is going to be making the highest contribution here. Anyway, that's it. I hope this was a little bit more clear.